This is a review of the major part of the lecture of 923 from Natural Disasters class about tornadoes. It's brought to you by Eric Clapton and John Lennon and Mitch Mitchell and Keith Richards, who called themselves the Dirty Mac for this one performance. The readings are relatively short because the author of our textbook tends to think of tornadoes as a small part of the overall topic of thunderstorms. I disagree. I think they deserve their own unit, but that's why it's a short amount of reading. Most everybody's familiar with what a tornado is. Swirling, intense winds, almost always associated with a thunderstorm, rotating counterclockwise, and has a center of a low pressure system. The tornado is usually a very small type of an event of a storm element. Usually the entire pathway that is exposed to very serious winds is less than half a mile wide, and many times only a quarter mile wide or so. The total travel path of a tornado is usually 20 miles or less. Some will travel a relatively short distance before falling apart. Some may last longer. Given the approximate average speed of a storm in general, including a storm that that contains a tornado, usually a tornado lifetime is 30 minutes or less, and probably many tornadoes form and die away in a matter of minutes before they cause damage, hopefully, or are even noticed. So a tornado is really a very small event, and that's highlighted by this particular diagram here, which shows with the red arrow pointing the size of a tornado, and the wall cloud, which is the slightly larger scale disturbance that eventually tightens up and condenses into a funnel. This has a very small size with respect to what's called a supercell, which is the by far the most common setting for which a tornado is likely to occur. A supercell, such as the one shown here, is of a size of perhaps 50 miles across. So it is an enormous storm. And it is actually really just a thunderstorm. However, it's one that, for all the reasons we described in the thunderstorm unit, lasts for a long time. Updrafts and downdrafts were separated for a long time, so the storm was able to grow to enormous size, and also there had to be a lot of available energy and moisture. So this is just the overall scale of a supercell. The anvil-shaped top, a place where the rising air might have even broken through into the stratosphere, and then within this overall storm, a rotating region that eventually actually condenses into a tornado funnel. So it's really, a tornado is really part of a much larger storm. And one thing that's significant about this is that it's probably the most significant way in which tornadoes can be anticipated, predicted, and detected is by first finding the very large and very prominent supercells that might be forming on a particular day or in a particular location, and then looking very closely at the supercells for conditions that might be leading to the formation of a tornado. The tornadoes are measured on something called the Fujita scale, and it has been relatively recently upgraded and updated and improved to be called the enhanced Fujita scale. It's really still the same. Ted Fujita was an original was the scientist who originally began to methodically study tornadoes, and his most important idea was that to learn about tornadoes, the best thing that could be done was to examine everything about the aftermath of the tornado and see what the damage looked like, what the paths looked like, the directions that debris were thrown, and all kinds of things that could be detected after the tornado was over. And it's really become clear that that's really the only way to study a tornado. It's too hard to both place and protect any kind of an instrument in a tornado. Because they're so unpredictable, it's hard to even get an instrument in the right place, and for the instrument to survive the storm is really unlikely. So the Fujita scale, going along with the philosophy of Dr. Fujita, bases the measuring of tornadoes on something called, is based on damage. It's called the Fujita scale. In the textbook, there's a table which gives a verbal description of the damage, which will associate with a certain scale, and an estimate, a very rough estimate of how fast the wind was going in order to cause this damage. But I want to make it clear again that the Fujita scale is not directly related to wind speed. The Fujita scale is related to damage, and by observing the damage and analyzing it, it's possible to take a guess at what the wind speeds are. I have a series of pictures which show perhaps an illustration of the damage that is caused by any particular, by a tornado of a particular Fujita size. EF0, a borderline tornado with serious but still believable winds, really causes light damage, and this picture might over exaggerate actually how much damage an EF0 typically causes. An EF1 rises to the level of actually causing serious roof damage. Cars driving can have trouble maintaining control in these winds. Mobile homes might even be overturned. An EF2 is the level at which a tornado becomes truly serious, and at such a point where large trees fall over, take out power lines, roofs are completely torn off of buildings, poorly built structures or weak structures are destroyed. And an EF2 tornado is about the wind speeds of a major hurricane. Moving up to an EF3, it's just a degree of damage, and these are wind speeds that would match or exceed the strongest hurricanes ever. And in this case, the damage is even more severe. And then just moving up the scale with whatever pictures, EF4 has a force of wind that is greater than any known tornado, any known hurricane by a considerable amount. EF4 will probably destroy everything in its path, and that still leaves an EF5 that will cause complete destruction of absolutely anything in the area, and even to the extent of picking up whole houses or cars and throwing them around. So that's the ultimate in violence in the atmosphere is an EF5 tornado. The ingredients for a tornado, one could say that the ingredients are a severe thunderstorm, or you could go backwards a step and say that the ingredients of a thunderstorm thereby become the ingredients of a tornado. In either case, you need a warm, moist air, moisture and heat, an unstable atmosphere, and some kind of lifting mechanism. But in the case of a tornado, it's necessary that the thunderstorm be a severe thunderstorm, or even progressing to an ultra severe thunderstorm, which we would call a supercell. Let's see. And finally, this whole idea of a supercell is in essence just a super severe thunderstorm which builds to a very large size and lasts for a very long time. It is possible for tornadoes to form in the eye wall of hurricanes in some circumstances, and some other clusters super strong thunderstorms, such as multi-cell clusters or mesoscale convective systems or squall lines, are also able to perhaps generate a tornado. But the most significant cause of a tornado is a supercell. And the last key to tornado formation is there must be wind shear, winds blowing in different directions in different places, that causes some rotation to develop, and that rotation can either be vertical or horizontal, but there has to be rotation involved in the system, probably caused by a wind shear. And I have more slides to show that later on, and that's the end of where I arrived at on Friday.